Hi, Carlos. Yes, please start sharing.
Hi all, can you hear me now?
Yeah, it seems to work. Give us 1 or 2 more minutes.
Yes. The audio quality is okay for you, or you want me to improve something?
Well, okay.
Okay, perfect.
Okay, I think we're ready to start. So that everybody back in here. So Carlos has given us the QR code. We can download his talk. Yeah. Okay, I think everybody's back. So let's get started. So our next speaker is Carlos Perez Sanchez from Heidelberg, and his title is Combinatorial Algebraic Remarks on Dirac ensembles and related matrix models. Thank you, Carlos.
Thank you very much for giving me the opportunity to speak here, inviting me. And yeah, so as Jim said, it's a little bit. I mean, I did some annotations to the talk, and if you want to have it cleanly, or yeah, I mean, yeah, I mean, you can just download it, because probably it's overkill that I put a lot of annotations. Anyway, so the talk is precisely that, some remarks on some matrix ensembles which are motivated by, I mean, some Dirac ensembles actually, which is yeah, I mean, a topic of this conference. And so yeah, it is based precisely on 3 works that will appear again. So yeah, anyway, so this is more or less the outline. So at the beginning, there's nothing. There is only a little bit of physical motivation, but it won't be physics. A little bit of input will be here, and a little bit of physical input will be here, but it's not emphasized. I will try to make the talk, I mean, address the mathematicians. And so I mean, non-competitive geometry is, yeah, I mean, in several topics, not everywhere, but I mean, random matrix theory too. A little bit less of free probability. Probably there's something that you might recognize that I didn't. That's probably one of the aims. And yeah, so that's one of the 2 physical slides I have. And it's indeed actually a motivation for physicists to be able to geometrically understand a theory which is incredibly successful. And this theory is described by a polynomial And this polynomial depends on certain couplings, so real values. And let's think that it has a lot of random variables here, let's say. Okay, so it's not exactly, in case you know what Faddeev goats are, then they shouldn't be there. But anyway, this polynomial doesn't get shorter. I mean, the classical Lagrangian of the standard model is the name. It doesn't get much shorter, and 100 terms actually can be packed in, I mean, can be obtained or summarized by these two terms in some very elegant way. And for this, I mean, this is not for free. You need a couple of principles there that the physical quantities you measure, they depend only on the spectrum of certain operator. This is a Dirac operator, like, I mean, it's a tensor-Fajon operator. And the input is precisely that there are 3 generations of particles on certain algebra, and you put this to the crank of NCG, and you get Lagrangian. That was half of the talk of John Barrett. And he also mentioned how, I mean, how the geometry puts very high, very hard constraints on the most general Dirac operator you might have. Here, whatever that means, you obtain this part of this polynomial I have shown you, whatever j is, by just taking the inner product of, let's say, the 96 fermions he put, like this matrix, and then again this one. So this means that if any of the entries of this 3-dimensional 0 was not 0, then you see in your polynomial some other fields that you don't observe in nature. So it's out of 10 to the 4 entries. It's okay. It's just responsible, the geometry of having these zeros here. So, and this is well, a nice motivation in physics. The thing is, that's not the end of the story. To make predictions, they use, let's say, textbook quantum field theory, advanced textbook quantum field theory, but it's not expressed in a non-commutative geometrical language. And they, I mean, 2 of the authors of that work mentioned in their book a far distant goal, which is to set up this functional integral, I mean, evaluation of spectral observables. Here, S is a certain spectral observable, and the aim is to be able to integrate also with this over this measure, which is faded, but this is at this moment is at least for me too ambitious, and also ideally you should be able to integrate over differential operators D, whatever that means, and that's a second simplification. So in this talk we will just assume that we're interested in understanding this measure, a measure of this form for certain f that will appear later. So this makes things not precisely easier, because usually I mean, people who are interested, for instance, in quantum gravity, they are confronted with this functional integration over metrics. I mean, even it's worse because not even the manifold this metrics live in is fixed. It also varies. And you are interested in a measure of this form for G for this action, essentially an integral of the curvature. And this paradigm shift means that you have to replace this functional integral by some operational integral.
So this was a quick question.
Yeah.
So D is Dirac, psi is element in the Hilbert space, spinor, and what is E?
E is a projector. Actually, you posed the question some days ago. Actually, it's a projector which selects the algebra. This is a constraint, the Lagrange type multiplier, that they play the role of selecting the algebra, because this algebra is an input. Okay, I mean, it selects the algebra. It's just that, but I cannot give you further detail. Just be above this equation, you can find the exact. It's a projector.
Okay.
Okay.
Thank you.
Thanks for the question. So the thing you shift this paradigm.
Sorry, Carlos, maybe I said, yeah, indeed, as you said, E is about fixed, varying the background manifold, basically.
Okay, great.
Yeah, so this is the idea. Yeah, thank you.
Thank you, Masoud. I guess you're Masoud. So, okay. Now, if you keep like Dirac operators at manifold, then this integral is even worse, right? So it's even hard to. I mean, it's really hard to define this, at least for me. And so one solution is truncating the spectrum of the Dirac operator. It's also something that has been mentioned by Barrett and Glaser already in their talks. And here's the possible application. Okay, I promised only two physics slides. And I mean, I will just move to math soon. So a possible application of this thing is Euclidean quantum gravity. Or yeah, I mean, you usually in quantum theory, you're for given 2 points, you want to compute the propagator, and not only the classical solution, which is, so to say, the geodesic between these two is what counts, but all the paths should be summed. Now you don't have a fixed background in quantum gravity, so you have to learn to make sense of the quantum superposition of these geometries, which is caricature, whose caricature is more or less here. I mean, initially by small perturbations, flat space, let's say, but you know, if you're ambitious, then you have to also add some instantons here. Whatever that means, the aim is also to be able to sum. I mean, to make sense of this quantum superposition of geometries, and this is not addressed today. It's just, I mean, the motivation. So this is the slide that probably is in any NCG talk. The origin of this discipline is a little bit also noncommutative topology, which is this equivalence of categories you already know. And then since this exists, then you can just think of unital, non-necessarily commutative sister algebras as the category of compact non-commutative topological spaces. But non-commutative geometry has more than non-commutative topology. It has some symmetric data, and it's interesting how these are implemented. Then you go back a little bit in history. Actually, what you can say is that the first theorem in NCG is Bayes' law, which tells how fast the Laplace spectrum grows. So if you order the Laplace spectrum, including multiplicity of certain bound region in Rd. So this counting function, so you fix the a large, use a real number positive lambda, large lambda, and you count all the eigenvalues with multiplicity which are below this threshold or the cutoff. And when you find asymptotic, well, Weil found asymptotically is that this scales with the volume of, some factors here, and the volume of the region, and lambda to the half of the dimension. So, which means if you know the spectrum of the Laplace spectrum, how it grows, and you can guess, like hearing this region, which the dimension is, but it does not answer positively Marek Katz's question, whether you can hear the shape of a drum. It tells a little bit of information, but you can, in non-commutative geometry, you can positively, let's say, answer this question. Actually, I learned this from Conrad Faisalicum, who also claimed that they can not only hear the drum, but they know how to hear the MP3 of it. So the story of today is not entirely unrelated. It's just, the motivation of the talk of today, it's more or less there, but it will be at the end will be combinatorics. However, I don't want to just introduce the physical way these ideas. So let's think a little bit about only mathematics. Okay, so you're given a space, a Riemann manifold, which is spin. That's important. That spin. Well, okay. You want a spectral triple, it has to be spin. And the observation is that you can replace the topology can be encoded here, and G can be encoded by the Dirac operator. It's obvious if you square it, you can rid of the G, the principal symbol. But the way to generalize this geodesic distance is interesting, because then you can test it with non-commutative algebra. So Geodesic distance is another way to compute this distance. So classically, classical commutative geometry, to make of M metric space, you take 2 points, you want to compute the distance, you just define it as the infimum of all paths I drew, which satisfies the conditions I drew here. So you throw all the paths and this tell you what's, measure the length and it tells you what the distance is, whatever. So how do you implement this in the NCG world? So you have to replace, I claim you replace G by D, and then it's better to have a formula which tells so. And it also nice the paradigm shift because you don't consider M, the manifold, as the fundamental object, but the algebra observables, it's the main thing. And this likes some communities in the algebraic side of the, some algebraic oriented communities, because you start with an algebra observables. So anyway, so the way to get it is instead of throwing all the curves, you throw all the algebra functions to certain states, in this case to pure states, just given by evaluation. And then you can, of course, you're in a vector space, you can just subtract it and measure how far they are. And you can get something interesting out of it if you put some condition on the gradient of f, which expressed in terms of the Dirac operator looks like this. So if you take you throw the whole algebra, you take the supremum of this satisfying this condition, what you reproduce is constants. So I say this is in the commutative world not helpful, but this is the basis of how you measure distances when you go non-commutative. So that's one of the ways to introduce this thing. And what you observe is that
maybe small remark: this dm of f is not the action of the Dirac on f; it's the composition of operator. As dm composed with multiplication operator.
Yes, f is acting on the. Okay, I didn't say this. It's important actually. C is acting as multiplication operators on the square on the Hilbert space of square integrable spinors. And so this Hilbert space is important because this is the arena where these two pieces interact, right? So it serves. It serves for the elements of the algebra to be able to interact with the Dirac operator. Yeah, thank you. So, so you observe that you actually have, this triple actually appears naturally. And so for general such manifolds, you get commutative star algebra, which is represented by the multiplication operators on a Hilbert space of square interval spinors and a self-adjoint operator. Well, essentially self-adjoint here, which locally has this expression. So and then you start proving facts about this. So for instance, for each element of for each smooth function, then this commutator is bounded, and in fact, for the coordinate functions, you get essentially gamma matrices. And then you start proving more interesting facts, which actually won't be entirely relevant for this talk because we work with finite dimensions. Sorry. Good. So then you do the same you did for Galfan-Naimark, and you start with this left side and go to the right-hand side just by dropping commutativity of the algebra. So spectral triple in the most elementary form would be just a triple of an involutive algebra represented on an inner product space, on which you have a Dirac operator, which has compact resolvent and such that this commutator is always bounded. Okay, it's not entirely necessary the whole definition because as I said, NCG. This thing we're doing was called initially random NCG. Just a disclaimer, it's just a very small discipline of NCG. Here stays spectral triples, and we do even less. So here's finite ones, and we focus on those finite ones which actually can be useful to represent truncations of space-time. So at least that's the aim. So what's okay? Question. Sorry. Okay.
Oh, there is no question.
Great. Okay, then let's go to the real topic. So Foxy geometries will be a spectral triple, right? But it's a little bit lengthy if I just put all the actions. And I mean, each one of the actions has makes sense. But okay, let's start from the characterization, which was very useful and was used by John Barrett. So a fuzzy geometry is determined by a signature. You fix a couple of integers, and this fixes a signature. I mean, just think about the matrix, which has diagonally p pluses and n minuses, and the elements of this fuzzy geometry are again an algebra, which by simplicity will just make it simple, but might be semi-simple. And this is just trivially represented on the Hilbert space multiplication. And this Hilbert space, I mean, the so-called finite spectral triples do not have this action, and here it's helpful because this will give you gamma matrices. Well, okay, some flavor space-time. I mean, S just has to be a Clifford module of this signature. Now, the theorem which appears here is that you can solve for the Dirac operator the actions. And once you fix conventions for the hermiticity of the gamma matrices, which are just endomorphisms here, and I mean, you can write the Dirac operators in terms of anti-commutators by a self-adjoint matrix, or commutators with a anti-Hermitian matrix. And whether this is the first or the former or the later, you determine by seeing at the product of gamma matrices that you form by, I mean, these sums run over multi-indices, and then each one has, I mean, you take the product or the product of all usual indices, and I mean, this resulting gamma matrix will be either self-adjoint or anti-self-adjoint, and accordingly you choose whether, I mean, your parameterizing matrices should be the former or the later. And these two examples appeared already in L stock, and they appear also in the paper. Okay, so in dimension 2, which is sort of Lorentzian dimension 2, you have two matrices, and yeah, so you fix this one to be anti-Hermitian, so accordingly you get this guy. But it gets interesting when you go dimensions higher, because some, at least in this dimension 4, triple products of matrix gamma appears. So here this hat means that you precisely omit the gamma mu from the product of the 4 gamma matrices, and for anti-Hermitian single matrices, this found to be Hermitian. So the accompanying matrix is this one. And there's with Masoud and Luc Verhoeven, we're I mean, trying to figure out what this means. Okay, like direction gravitation, and so okay, we out of these commutators and commutators you get double traces, and okay, so it's needed how to compute these traces, and there is a combinatorial formula to do this, and what helps here is just some very well-known fact, at least if you compute some Fermion propagators, whatever, is that the traces of gamma matrices, I mean, this trace on the left can be different from 0 if pairwise to indices agree, right? And I mean, this can be represented by these things. So this eta is just the signature, just a diagonal matrix with pluses and minuses, and for each couple of bilinears, you can associate a core diagram. I mean, it's trivial, right? So for each crossing, which comes from, you know, having to commute because this guy is the gamma matrix is anti-commute, having to pass the gamma matrix from left to right, and you get a minus. So this suggests that you can, and it's true, organize the spectral action. The spectral action that makes sense to quantize in this setting is a polynomial, and this has already been discussed by John Barrett, and also L discussed this. Okay, so if you know what this, then you know for an integer t, then you know what the spectral action is for this class of geometries. So this is just a combinatorial formula. So it's not important to understand it completely. I will just spell it out, but what you should observe only is that you get these double traces in a pretty much natural way. So here, this sum just runs over multi-indices, which is not very important, but if the associated, differential form on RT, when you put this multi-index here, does not vanish, then you put the index here, and this minus means that, you have all, these multi-indices have all single indices, only many. And then you get the sum by the corrected chord diagrams here. This is one of these chord diagrams. So that's not the interesting part. The interesting part is that then you get a sum over all the power set of 2t. So this sum over power set determines whether the matrix gets out, outside or inside one trace. Determines the matrices that are inside one trace and which are outside. So this is this green term here. So from these two trivial partitions, so the empty set and the complete set, you get this natural scaling here. So it's not important. The important thing is you get double traces, right? And then you get also several independent matrices that will be random, so you get contact to the community probability. Okay, so a warning is that if you come from the physics, it's obvious for you, but I'm trying to say, okay, I apologize for the saying obvious things, but these are not Feynman diagrams. So we're used to expanding Feynman diagrams. So these are just chord diagrams, and these just organize the classical action, right? So Feynman diagrams rather look like you're putting some hairs around it, and okay, which do not always make sense. But if the ending points coincide in color, here you have a sum over colors of these are colored, and okay, if they agree at the end, then this makes sense. But it's just a remark that you shouldn't think of these chord diagrams as Feynman diagrams. So the main point is that you are given a chord diagram, and this chord diagram determines an element in the free algebra. Okay. So before going quantum, let me just do some remarks. Here, you're interested actually in convergent, in the terminology given by Guettin course. You're interested in convergent ensembles of Dirac operators of fuzzy geometries or matrix geometries. So by this, it is turned out to be parameterized as such, and the result here is also, to get this result, I also used some observations, very useful observations in the paper of Barrett-Glaser. So the thing is, the observation that these are not noncommutative polynomials is obvious. The hard thing is to determine the precise coefficients. Okay. So this Dirac, let's say moduli, but it's not moduli because you're not moduli now. So it's just this space of Dirac operators is parameterized by products of this algebra and the space of Hermitian matrices, and then this have a Lebesgue measure. And these are given in terms of certain noncommutative polynomials, right? Now it makes sense also to study the combinatorial problem associated to Dirac ensembles. So I also try to understand Dirac ensembles, but for the rest of the talk, I will a little bit shift the interest to the combinatorial part. So let's think. Even I won't keep mentioning this, but that this will be formal. I mean, generating functions of color-driven graphs. So I don't know how big your screen is, but in case it's not big enough, here I just let me zoom. Here you have interactions which appear actually in this computation for the two-dimensional case. And this word determines precisely how you should order these colors on a wheel, let's say. And to the whole wheel, it applies. I mean, we like to label these wheels. And these G's here are the T's in Elba's talk. And the T's, I don't remember if Gaetan also used the T's as coupling constant. Probably he did. And also in the double trace, multi-trace type of interaction, they should appear like, you shouldn't think that this G2 only applies to this part, but this G2 sits somewhere in the wheel and it applies to the 2, because obviously this guy is linear, it should be able to enter this 2. Anyway, no, I don't know how to enter. Okay. So let me not mention the physics part, but repeat that this kind of in this case, it's a cylinder, but it could be also that these sort of interactions lead, I mean, are leveling higher topologies. I mean, with more boundaries. These are generating. I mean, these are the building blocks of stuffed maps, which have been already mentioned by Gaetan. And also, they appear in. I mean. Things that appear here appears also in probabilistic works by Guillaume Sepin and David Deppel and Wu-Chen Li and Dmitry Shevchenko. And also by Guillaume, but probably several also. Okay, and also in holography, which I'm not mentioning here. So these trace polynomials will appear, so if you're curious. Okay. So this thanks Octavio for the reference, by the way. So then these guys are just dual, as you know, to the graphs. In fact, this guy is just the dual of this piece here. So you're interested now in understanding. I mean, I haven't done work on maps, but this is a possible research direction that to try to understand how to enumerate this kind of maps, which are phase-ordered. Usually, you know the two-matrix model, which is very relevant in enough solution to the Ising, I mean, to the Ising model, to the Ising model. And this has a different feature. You cannot hear color uniformly one phase. I mean, you have each one color for each word, let's say. So you keep track of these things, and I don't know how to simplify. I mean, to get rid of this word, which is on the boundary of each of these fundamental domains. Okay, so I'm not doing very good with time, so let me skip again the physical motivation. It's very nicely written in a paper, but what I'm trying to say here is that, I mean, probably not as in the sense of formal matrix models, but I mean, you have to do convergence, analyze convergence, whatever. But probably it's useful to look at the renormalization group, since this can, I mean, a linearized RB flow with the fixed point looks like one of the conditions that implement the double scaling limit, I mean, which people know from last century in 2D quantum gravity. Okay, so let me skip this physical motivation and go to the combinatorics. More or less, what this other diagram means is that, I mean, I'm trying to just tell you that I left the very small, very thin moduli of Dirac operators, and I just went to a wider. I mean, the flow I obtained does not keep in this space, which would be nice, but I'm considering now more, I mean, wider and independent interactions. in this huge theory space. So I mean, this slide is not, I mean, if this doesn't tell you something, don't worry, because what comes does not depend on this. So let's then try to do something. And okay, let's just not use the physical notation for expectation values and respect the probabilists. And then just, you know, I guess you know the theorem, which was proven by Serlis before Dick. And so for zero mean variables, you get that you can expect this. You can express these expectation values in terms of pairings, and this is relevant. I mean, so another part another part of the notation I want to fix is the number of Hermitian matrices that I will be considering. And I mean, usually in probabilistic papers, you read the whole time this n. But I will use Schneid's notation, which is like, you know, you fade a little bit the n, and sometimes it will disappear. In my case, I will not always keep track of this, but I mean, keep in mind there are matrices of size n, and I mean, it's never bad to put a second example of what we have already seen, and it has been mentioned many times, the 1/n expansion. Here for a correlation which satisfies this condition, which I mean, for Hermitian matrices is having this Gaussian term in the measure with some normalizing factors. Actually, it's wrong. It should be 1/n here. And if you put 1/n, then it fits. Then the expectation value of this trace of a commutative polynomial, of this non-commutative polynomial, is just one graph. And I mean, this graph lives on a surface, and if you split these ribbon graphs by here, you can just see that one side is a torus and the other side is a torus, so it should be an oriented Riemann surface of two holes. And this scales with the Euler characteristic, which is -2. Okay, that's a way to compute these guys. Anyway, so now this is the kind of Feynman diagrams you get. And now you're interested in another question. So this is also kind of Feynman diagrams you get in a 5-4 theory. But now my 5-4 theory has, you know, labeled, I mean, it has 4 ribbon edges, and each one of these has possibly columns. They might be the same, but in this case, it's, for instance, A, B, C, D, or X1, X2, X3, X4, whatever. So these are examples of Feynman diagrams, but we won't go this wild. Actually, for renormalization, the type of functional renormalization I will be addressing, it's enough to consider one loop graphs. So one loop is just what your mind says it is. So in this case, just in this toy example, the feet can just join, and I mean, the main thing is that the letters coincide. So actually you can, I mean, point out inside the circle with one hand and with one leg, the opposite leg to outside the circle, and would be a valid chord in here, a valid Feynman diagram. Now, one way of looking this functional renormalization thing is just decimating and sort of erasing. I mean, this is not put very correctly in with mathematical rigor, but it's just a hand waving. Okay, one way of interpreting a functional renormalization in terms of maps is just sort of erasing very small details about your surface or your maps, and this is done by just doing this contraction around the loops. So if you erase this loop here, you would get this higher order interaction, which a larger word, so to say. And I mean, the same will be here. Just like you also can erase a loop which gives you a not higher degree interaction. So it sort of washes away some very microscopic information. I mean, this should be studied in detail, but that's more or less the idea. So actually, if you began with some very simple words, this flow will start generating a lot of words again. And for instance, in as a first talk about block topological recursion and Dirac ensembles. If I don't remember, at least in the paper, because I read it, they used with Masood more traces than 2. And so renormalization is, in Dirac ensembles, you have only 2 traces, but this third trace or higher, it comes from renormalization in very natural way. So the question, which is very sloppily formulated first, is so given an operator, I will be calling operators these traces of free algebra elements, find up to given degree of, of the couplings. Couplings are these parameters which label these words here. All one loops it comes from, as in the above example sense. So you can label the legs. You can pick a dictionary, pick a word in this dictionary, and after labeling the legs of the allowed alphabet for these guys, you can ask for all the formations which have a one loop. And this question is relevant to renormalization, at least in this flavor of renormalization. At the end you will end up doing analysis, but this combinatorial approach is at least in a first approach is good already. So a little bit less sloppy is it's a fact that quantum theories flow with energy. You can see this for, in matter, right? So what does it mean? Does they flow? They flow in a renormalization time, which in this theory turns out to be the logarithm of the matrix scale. And what you should think of is of having introduced a microscopic description at a very high scale, Corley n. And for example, for the 2-matrix model, for one of the many 2-matrix models, the Bayes reaction would be, for instance, this one. Let's put a polynomial which is genuinely non-commutative. And what you cannot avoid that this guy generates just all the compatible operators. So for instance, one of the corrections you have to add this guy describes the theory at this very high scale, and this guy describes the theory at the new scale n. So so this guy generates a new trace, because if you read the non-contracted edges around the loop, you have A, B, B, and in the inside you have a trivial word, which after you trace it gives you this factor n. So to the theory you started with, you have to add a lot of operators here, which are called relative corrections. And now at the scale n, the new couplings, the new coefficients of this guy, they start running. So this might be a function of n, the matrix size. But I won't get of this and factors. They might be just absorbed in the couplings, and the end. They should be scaled correctly. It's not the point of this talk. So you're interested in one loop graphs, and the way to form the effective vertex, which is what you saw here, is just to read. Let's go to the drawing. Actually, it's just the words here. So you take this kind of constellation of interactions here, and you put it. They are on a loop, and actually you begin from the right hand side. You're interested in 2 words, usually in 2 words, let's say. And you want to know, okay. So if you're given this configuration, then you form these 2 words, W1 and W2, just by reading off the word you find inside, and in the opposite direction, the one you find on the inside. So you're reading the labelings you have at cylinder. So, and the interesting question is, rather, if you fix the right-hand side of this drawing, which are all the possible operators that enter here? Okay, so you have to list these guys, and actually it gets a little bit more complicated. Well, it's less trivial, because if you have that these guys are allowed to be multi-trace, then there is a subtlety that the topological one loop condition is not the same as a quantum field theoretical loop condition. So topologically, this is not a one loop, because this guy is sort of disconnected, but this is to be interpreted as a cylinder, right? So So this G2 is joining these two pieces, this trace of a third degree polynomial with this fifth degree polynomial. It's joined by G2. And so this has to be considered as a one loop in the quantum field theory sense. And then the question here is different because you have different contributions, right? So once you have the list, and you have to sum the products of this guy you find here, and these polynomials span, I mean, the beta function, the so-called beta function of O, which is the one which determines how this theory flows in some simplified state. So there are two steps or two approaches, let's say. So once is you start proving your beta equation, whatever, and then in this case, I mean, the proof, of course, determines which algebra you should use, etc. And then define the way I just mentioned, the beta equations. I mean, in this case, the experiment which was performed here was to put 48 operators. You get 48 operators at degree 6, and after that you truncate everything. So that's one of the effects of the theory, that you have to work with truncations, but this is otherwise not possible. So in here you get a real solution after you impose several. I mean, after you impose that these solutions should be real and a single relevant direction, which means that this matrix has only one positive eigenvalue. I mean, doesn't matter. It's just a way to choose precisely one solution, and if you do so, you get a certain agreement with a result of Kazakov and Sanchez for the ABAB model. So this ABAB model has interactions A4 and B4 and ABAB. So okay, but I don't want to talk about this. I want to talk to you about certain algebraic property of flow, and you can do the other way around. I mean, to sort of find unicity of this result, whether this algebra used here is correct. At the end, it's just the matrix algebra, but in some intertwined way. Okay, so you write down the equation. It's a little bit pragmatic, which is what you want. And then you solve this equation for the algebra. So you write down the equation. I want the equation. So which should be the algebra A that makes this equation true mathematically? So you sum. Okay, that's technical, right? So imposing the one loop structure, and then you can solve for the algebra. And so the claim is that this algebra is unique. And I mean, the algebra that competes with this equation is unique. And let me then tell you which is this thing. Here appear some tools which are used commonly, or actually appear first in free probability. They're also called free quotient model. But let me use the NC derivative name. And so for one chosen variable, matrix variable, actually you can do it with a matrix. So it's an abstract thing. So you take the free algebra in K generators, and then it's an operator from here to here. And this NC derivative is just a sum of replacements of A appearing in a word by the tensor. So if you take par, PAR, then you replace A twice here in the middle, but at the end it's not possible, so you add a 1. So it's not a crazy rule because it comes actually from deriving matrices, but okay, let's just keep it abstract here. And so I probably cannot make the link with the nice lecture that Gaetan just said about loop equations and how these are just precisely related to the analytic form he presented. But they start from the same fact, so they should be actually equivalent. Probably they will mention also in the Nathan talk. So this NC derivative enters here, and it also enters Voiculescu cyclic derivative, which I mean the rule for this guy is you can infer it by applying the derivative, the usual derivative to a trace of a matrix. So let me not define it. So, but I'm interested in higher degree differential operators. In this case, the Hessian, noncommutative Hessian. So you pick a word like in this. I mean, don't look just two derivatives, right? The entries of the Hessian. It would be a matrix in this algebra essentially, where an algebra with two entries. With entries this variant of this relative to the free algebra. And then it's better understood with just an example, right? So if you put this octic polynomial, and you can just understand this guy, the entry of this guy by cuts. So from the variable you first derive to the variable which the second you derive. So from A to B, and then the rest of the word you just have to write it down. And these cuts might also traverse cut into two non-trivial paths this word, in whose case you have to put one piece on one side and the other piece on the other side. So actually, this is just a symbolic thing for putting A on this big parenthesis. From this term B A as monomial, right? So yeah, whatever this is useful then for normalization. So the thing is that you then have this product of traces, and then your algebra has to be extended. And one way to see this is that here you have a second degree polynomial, and if you derive it, you put the Hessian on it, then it has to be the entry CC has to be the identity because of graphical representation. If you derive twice this thing, it's just a propagator. But if you take the other operator, which is taking the trace first and then squaring, this is quite different thing. So this should be also a constant, which generates some constants inside here. So these guys, as vector space, are the same. This is just a tensor product of two algebras, but this will be an algebra. So there is a second. There is another different sign for this second product. So this guy just yields an ordinary unit, but this doesn't. So then the Hessian, the thing is that the Hessian is not expressed just in terms of this usual tensor product, but it implies this second one. Then having this, you can write down this equation. So it implies being able to compute derivatives of the action that describes your theory at scale n. And here's my multimatrix, my K tuple of matrices. And if you derive this guy, you get the beta functions on the left-hand side. And how to derive the right-hand side is, that's the claim. But this is not my equation. This is Bette's equation. So these things in blue are for this talk irrelevant. It's subtle, but it's irrelevant. And there is these are just form functions, which tells you how you have to decimate degrees of freedom from the high scale to the lower one. But this is not for combinatorics essential. But it's more or less, these derivatives appear. So let me just split the essential part, which is this regulator independent part, from this part, which is not interesting for now. So actually, this is equivalent to projecting to the flow to UN invariants. Okay, this is a simplification, but it's the only way I see of computing. So this guy is just expanded as a geometric series here, and that's where you get these things from. And then the thing is to determine which is this star thing. So, and you get this guy from knowing first which the trace is. But to use this, you use tadpoles. You look at the tadpoles, which are just contractions of one single vertex. Usually they look like this. Okay, so you can construct your word such that what you get from this equation is only correct if the trace you use here. The super trace that appears here is just the trace of the it should be MN, the matrix trace, with entries in this algebra. And then so this is the way to determine the matrix trace in this algebra. So if you take PQ, usual tensor product, then it should split. But if you take this square product, this box product, then it doesn't. You first have to multiply, and then you take the trace, and there is no factor n here. But these are not dying. I mean, in the large and not necessarily. I mean, if you compare these guys directly, they do, but they will be alive in the flow. Okay, let me not tell you about the proof, but tell me, because then there is no time for questions. So let me give you not the proof, but the claim. So I have 5 minutes. No, I don't have 5 minutes. Give me 2 minutes. Is it okay?
Start a little late, so you have 5 minutes.
Okay, thank you. So ignore please these diagrams. I just should have spoken a little bit faster, or put less material. And so the claim, well, the observation is that assuming that the renormalization flow is computable in terms of UN invariance, then the algebra of functional renormalization, let's say just the algebra which makes the flow computable, is this algebra of matrices with non-commutative entries, where this algebra is just 4 copies of the free algebra distributed this way. So as a vector space, this is just the tensor product, just like this, but it has a different algebra structure. Everything comes from the algebra of matrices, but anyway, it's a very useful for computation, this observation, right? So if you have 2 products, so if you want to multiply 2 elements, you have to tell how to perform 4 types of products. So circle, 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 box, 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 circle, box, box. And these are given by this formulae. Okay, so why you get this formulae, then it's in the proof. But what completes the description of this algebra is precisely the traces which have already been mentioned. Okay, before giving you an example, let me just be a little bit more precise, because it's not quite this algebra what appears here. What appears is the algebra of so-called trace polynomials, which actually is combinations of this form. So you're allowed to have both generators of free algebra as these guys inside a trace, right? So traces of non-commutative polynomials and accompanying non-commutative polynomials. And okay, but here you don't have any differential operators anymore, so it's safe just to state the claim as it stands now. Okay, so then I have an example, but I like this example, but where it's clear that instead of working with graphs, you just can put these guys to the computer, and each one of these entries of the Hessian has an interpretation in terms of graphs. And when you trace the Hessian, you get all the possible graphs. But okay, I think it's just to be careful with questions. Then let me just conclude. So we saw that the spectral triple is a generalization of a manifold whose commutativity has been dropped. This is useful in physics in order to understand gauge theories and the standard model. And the interesting structure there is a spin manifold times some finite spectral triple. At least the claim at a classical level is true, and one is interested in quantizing this claim. This was not mentioned actually, but some aspects were tangentially at least touched. We're interested in this measure, DD, weighted by the spectral action, and this was a little bit tangentially mentioned. So, and the algebra that is useful to compute functional renormalization was determined, and it turns out to be a factor relative of the free algebra. And yeah, thank you for the attention. I'm sorry for being a little bit over time.
Thank you very much. And
Thank you.
yeah, do we have any questions or comments from audience?
Hi, Carlos. Thanks for your talk. So,
Hi,
yeah,
Maximilian.
hi. So, can you explain a little bit that the Wetterick equation? I mean, how this relates to these sort of matrix models here, maybe? Yeah.
I mean, here I just kept doing this mathematical, I mean, this combinatorial problem. So I actually, of course, I started the paper like aiming at understanding the renormalization flow for the matrix for the Dirac ensembles, but I didn't succeed in this. So what I'm renormalizing here is just matrix models whose couplings might be fluctuating independently. And if you have Dirac ensembles, then these couplings are related. So for instance, I guess twice the coupling of AB should be the coupling of A squared B squared, something like this, or 1/2. So these couplings should flow together, and my flow does not achieve this. So that's the failure part. The less failure part is that this makes sense for more general matrix models. So probably there is a way to implement something that the flow it stays. I mean, some constraint that makes the flow keep. I mean, that to keep the flow inside the Dirac moduli, which is not achieved here. So I don't know. Probably, I mean, if working with formal series, I think you're not very confident to. I mean, you're not very happy to explore their phase transitions, for instance. But who knows? Probably.
Okay, very good. Thank you.
Okay. If the question was to tell you something more about the Wetterick equation itself, I can do it. But probably I should have started with the claim that it's not the Wetterick equation for Dirac ensembles. That's what I wanted to say.
Now. Yeah, thank you. Yeah, that's fine now. Yeah.
Okay.
Does anybody else have a question?
I have a question, very general. In fact, as you mentioned, this ultimate goal would be to define this functional integral over all possible Diracs. So you really mean over all possible Diracs, or only over those Diracs which consist of this finite part in the standard model description?
No, here is really meant. Okay, here is really meant understanding this integral. So whatever this is for general Dirac. So it's, I mean, as it's written in here, it's really for a Dirac operator which has both this finite part and the differential part. But this is a shortcut to that. I mean, it's not obvious why this should be related. These integrals we study should be related to this integral they want. But so morally, this should be the. I mean, morally, what wants to claim is that this integral they look for is the large limit of the integrals we look for. Probably there is some phase transition to some manifold regime, which probably will be mentioned next talk. So I mean, the claim of
like an approximation of a manifold with its fuzzy version, yes.
Yes. Yeah, we deal with approximations of this integral, but the aim is to understand it, fully.
Okay. Okay, thank you.
Yeah, thank you.
Any other questions from the Zoom audience? Okay, maybe I'll just ask a question about these chord diagrams.
Yeah.
So you were counting the number of crossings. Is that what the exponent of chi was? I think it was slide 9 or slide 10.
Yeah. So this number of crossings, I mean, you assume transversal crossings, so you can count these guys. And
right.
They appear, but they are not but a sign. So I mean, this gives you exponent to the number of crossings somewhere. And
right. So there's this idea of a cuniform Fock space where you also get count these things. Have you?
Okay, sincerely, I don't.
There's a recent paper of Roland Speicher and well, somebody else. Whose name?
Okay.
Yeah, that's right. Yeah, a student of Benoit Collins, exactly. Yes, I mean, they just used these chord diagrams, but they had some things about the combinatorics of them that might be relevant.
Great. Good
Yeah,
to know.
so the model was a Q-deform Fock space. That's where they came. That's how they arose in their work.
Okay.
Q-deform Gaussian operators and Q commutation relations.
Great.
Those things. Okay.
Great. Thank you for the reference.
Yeah.
I will look at it definitely.
Yeah. Okay, so it looks like we're done for the morning. So thank you again, Carlos.
Yeah. Thank you all for have a nice conference still. Bye.
And we start again at 2. And I think Nathan will talk at 2. Okay, so now we have lunch. Okay.